Hello students, welcome to the 64-bit edition of the Security Tube Linux Assembly Expert course and certification. Now in this video, we will discuss what is assembly language. Now students who've seen my 32-bit SLA video series, you may find a lot of slides common simply because I've decided to keep the flow similar to what we did in the 32-bit version. However, all discussions here will be about 64-bit assembly language only. Okay, great. So what is assembly language? Right, so very simply put, it's a low-level programming language with which we humans can communicate with the microprocessor, and typically this language is processor family specific, right? And at the very same time, most assembly language instructions may have a one-to-one correspondence with the machine code consumed by the microprocessor. Now, what does all of this mean? Very simply put, your processor does not understand English or even assembly language for that matter. It can only speak binary. Unfortunately, we can't. And this is where assembly language acts as a bridge between what we want the processor to do and then finally translating that into a language which the processor understands. So we are going to speak in assembly language. The assembler and linker will translate that into what is called machine language, which can be easily consumed by the processor. So what is the correlation with high-level languages? If you take a language like C, which is still super popular, we write the C code which the C preprocessor goes ahead and converts into the preprocessed code, which the compiler takes and converts into an assembly language format, and then the assembler goes ahead and converts it into object files, and then the linker takes those object files and other things like libraries, relocation information and whatnot, and then finally creates the executable. So let's go ahead and take up a very simple example of using an assembly language program and going through the whole process of assembling it, linking it, and then running it, right? So all of you should have your 64-bit Ubuntu up and running. I'm using the 12.04 LTS. If you haven't, view the previous video in the series and go ahead and install it so that you can follow me along. Now, we do not have all the tools which we require at this point to go ahead and assemble, link our programs. So to do that, let me do the installation real quick. Sudo apt-get install NASM, which is the net-wide assembler, and then build essential. Enter the password, and this is 31 MB is going to be utilized. Let me pause this video while the installation is happening. Okay, and we are back. So the installation should have finished, and once this is done, you should find that you have NASM and you have LD as well, which is the linker. Awesome. So now let's actually look at a very simple example of an assembly language program. And because this is really a shell coding course, I'm going to pick up a piece of shell code and then let's go ahead and assemble and link it, rather than me just using a general purpose assembly language program, right? So for this, let's head over to our friends at shellstorm.org. When I say friends, I don't know Jonathan personally, but I think he's done a fantastic job going ahead and cataloging all of this at shell-storm.org. Let me open up the shell code database and let's scroll down to Linux, and here is the Linux x86 64 shellcode. This is really what we need for 64-bit shell coding. A lot of good examples. And interestingly, when I open this page, I noticed, just have a look at the number of 64-bit shellcode examples for Linux, and then just look at the number of examples for the 32-bit version. It just goes on and on and on, right? Incredible. So now you know that at the end of this course, you'll probably be, one of those few people who can do 64-bit shell coding, because looks like the percentage of people doing 64-bit shell coding is much smaller than the percentage doing 32-bit shell coding. Now let's do the following. Let's go ahead and open up this shell code by a gentleman called evil.xi4ou. So let's right click that, open it up, and here is his bind shell code, right? So what this code is going to do is just go ahead and bind to port 4444 and probably wait for an incoming client, and here is all the assembly language code. So if you've never seen assembly language code before, well, this is really how it looks like. And if you notice, I mean, this is just like any other, looks like any other programming language like Python or C, just that the actual syntax of the different keywords, etc. is different. Let's go ahead and now copy and use this code and go through the process of assembling the whole thing. Looks like my mouse isn't working as desired. Let me make this smaller. And now let me actually go ahead and copy this. Please ensure that you are copying only up to the syscall and do not include, the close comment tag. And you start from bit 64. Okay. You may end up making a mistake, and the NASM the NASM assembler will go ahead and complain for a syntax problem. So let's open this up. Now you can use any text editor you like. I'll probably be alternating between Pico, Nano, Vim, and whatever is available on the system. I think Pico is available by default. So let's do a Pico, let's say demo.nasm, and let me paste all of this assembly language code. Scroll up and verify everything is fine. Fantastic. Save it. That's Control O, hit and enter. Control X to exit. Right. So you should actually have a demo.nasm inside your existing folder. Now, typically an assembly language file to an executable is a two-step process. The first step is to assemble it and to get an object file. And the second step is to give that object file to a linker which can link it to the final executable. So let's use NASM. Now the important thing to note, if you type in NASM without any arguments, it would say -h is what is for help. Let's do that. The important thing is we want to go ahead and ensure that NASM will only generate 64-bit shellcode eventually, or rather 64-bit object file. To figure out the different options available for output format, use the -h option. So NASM -hf, and these are the different output formats which are there. The one we are interested in is ELF64, right? This is what we are interested in. So now let's say NASM -f ELF64 demo.nasm -o for output file demo.o, and right now you would notice that an object file has been created called demo.o, right? Now we need to go ahead and convert this object file into an actual ELF binary, and that can be done using ld the linker. And we're going to say ld demo.o -o demo. And you see a little warning here saying, the entry symbol blah 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 could not be found. For the time being, don't worry about it. We'll talk about entry symbols and all that a little later. So now you should have the actual binary, the object file, and then the original assembly language file from which this came. So if you go back and look at the description of the shellcode, he says this is a bind shell to port 4444. If you've never heard what a bind shell is, try looking at my Metasploit videos, which are also posted on Pentester Academy. So let me run this program /demo. Now hopefully this has gone ahead and locked itself to port 4444, waiting for a connection. Let me open a new terminal. And you don't need to do this. I'm just ensuring my prompt is that of Pentester Academy. And if you're wondering why, unfortunately, a lot of times all this premium content, which takes me really hours and hours to make, is pirated, passed around. So at the very least, I want people to know where it came from, right? As sad as I get when things get pirated, but hey, that's life. So let me kind of go back in here. Okay, so now let's first look at if we have a process listening, and to do that we can do an T. We do a quick netstat and we can clearly see that there is a process listening on port 4444. Now let me use netcat to connect to that port. And really I could have connected from some other machine as well, because it's listening on all IP addresses. Here we go. Let me do a PWD. Let me do who am I? Pentester Academy and ls. And pretty much what we have there is a bind shell. Exit should exit. So this was a very simple example of A, how assembly language looks like, and B, how to take an assembly language file and then finally create a binary from it. And in between, we go through an object file. Now, basically, let's try and understand the situation a little bit more better. So we're going to use a tool called object dump. And I'm basically going to say -m Intel, because assembly language format can be Intel or AT&T, the syntax, and then give it demo.o, and you would see the whole assembly language dump coming back in here. Now what object dump does is it looks into the object, picks up the different sections, and then goes ahead and disassembles them. That's what the D stands for, right? Disassemble all sections. Now this gives us a very clear picture of what we are dealing with. Now I said XOR EAX is really what assembly language is. However, the hex equivalent 31C0 is pretty much what your processor understands. So when the processor gets a 31C0, it really knows it needs to do a XOR operation using the CPU registers EAX and EAX, which is pretty much just XOR EAX with itself. If you've never heard of registers, etc., do not worry. I think I'm going to be covering them shortly in the next couple of videos. Similarly, XOR EBX is 31 dB, and if you notice, the XOR instructions seem to have the first byte 31 constant, while the second byte varies depending on which register combinations we seem to be using, right? So the cool part here is that your processor understands 31 dB to be XOR EBX, and because of using assembly language and then the assembler and linker, you do not need to memorize that 31 dB is what will make the processor XOR the EBX register with itself, right? So hopefully this should have acted as a very quick introduction to assembly language and how assembly language looks like. In the next video, we'll take things more further ahead. That's all for this video. Thank you.